Welcome once again to this course in optimization. Today we are going back to our study of quasi-Newton method, which are by the way very effective methods. Now this is the problem that we really intended to solve, because we had a matrix Bk and we now want to improve from Bk to Bk plus 1 such that Bk plus 1 would be symmetric, satisfy the second equation, as well as it has to be positive definite at the end. So, how do I do it? Okay. Now, how do you choose the norm of a matrix? Now, because I am taking symmetric matrices, in the case of symmetric matrices, there is an important norm. So, if you have a matrix A, there is an important class of norm called the Frobenius norm. And this Frobenius norm can be actually written as the trace of A and you take half of that, right. Now, of course, this simply means that you can just write it down, right. Now, because if you have an n cross n matrix, you can write down this as summation if all the elements of these are Aij. So, you can write them as Aij square, where I and j are varying from 1 to n. Now, usually in practice people have used what is called the weighted Frobenius norm of a matrix. So, it is called the weighted Frobenius norm. Now, the weighted Frobenius norm of the matrix is defined as the matrix A multiplied by a weight. Now, I would like to remind you why we use this symbol w to the power half. So, what is that? Square root of a matrix? Precisely. So, these matrices are PSD matrices, right. Usually these are positive semi-definite matrices. So, what it means that if you give me a positive semi-definite matrix, there is a famous result, if A is positive semi-definite, then there exists a positive semi-definite matrix, PSD matrix symmetric. A is a n cross n symmetric PD positive semi-definite matrix, then there will exist a symmetric positive definite matrix B such that A is equal to B square, or B is usually marked as or denoted as A to the power half. So, with this that is the meaning of this W. Now, usually W is so chosen that if you take a matrix like this, basically then if you look at this matrix B minus B bar or B minus Bk, so you really have to choose, we want the weighted thing. So, it should be W to the power minus half. So, this is not the only way to do it, it's okay, but this is one of the ways used in practice. So, we are just showing one of you this approach, but it might be quite difficult for a beginner. So, we will not just go into too much details, give you an idea about what would go on, and then take a simpler version of the problem and give a solution which Goulet has given, which is a simple and beautiful solution. And once you see that, you can really appreciate and understand what has happened. So, if you take a W like this, we expect W to satisfy Wyk should be is equal to Sk, which is nothing but the reverse of, it is nothing but the reverse of the, because if Wyk is Sk, then of course Pk Sk is Yk, this can be Yk and so on and so forth. So, sorry Pk. So, this is what you would expect, we expect this to happen. And how do you know what is your W? So, usually W is given as the inverse of the matrix Gk inverse, which is called the average Hessian. And this has a particular formula which says you are basically integrating out the Hessian matrix. So, you have taken the matrix and integrating it out term by term. Every term of the matrix is integrated, and the new matrix means this is now a matrix. G is a matrix whose every term is some sort of an integral of this. You take the Hessian matrix, term by term you integrate. Right, this is Xk minus Xk plus 1 into d tau. Now, if you choose something like this and try to optimize this problem, get a solution to this problem, then your solution becomes, so if I call this problem as Qn or the quasi Newton problem. So, the solution of Qn is I minus Yk Sk transpose divided by Yk Sk. Looks elegant that such a complicated looking thing would give such a nice result. So, these are matrices. So, if the starting matrix B naught is I, then B1 is product of this, right, product of these two into this plus this. Now, this sort of updating moving from Bk to Bk plus 1 is called the Davidson-Fletcher-Powell update or Davidson-Fletcher-Powell method. So, the upper one is called Now, the question is how do you actually solve this problem, the weighted graph problem, or how do you actually solve that problem? That is a very important question. And if I really want to solve that kind of problem, it is quite difficult, and in the sense that it's bit involved, and it might be the scope of, it might be beyond the scope of this audience, which is a mixed one, I guess. So, I will look into a much simpler version of this problem, which I take from Goulet, Osman Goulet, Foundations of Optimization, and with that simple problem, I will try to solve that simple problem, leaving the difficult job to you, of course, but let us look at that simple problem. So, simpler version of problem Qn due to Goulet. Now, let us look at this problem. See, we will just look into this problem. So, we will take an x, so we will consider, now the problem is on the space Sn of symmetric matrices. So, we will minimize a matrix n cross n matrix X using the Frobenius norm. In fact, I will minimize half of the square of that, such that X times A is B, where A is an n cross n matrix and B is an n cross n matrix, and of course, we do not expect B to be 0, B of course, we will expect B to be non-zero and A to be non-zero too. So, let us just take for the time being. So, X is my, so this is a structured optimization problem, as Goulet calls it. So, we will just write it down here as this is a structured optimization problem. In fact, I have a query to give you. Here as a homework, can you take this? Can you show that Bk plus 1 is positive definite if Bk is so? So, take this as a homework. Now, we are going to look into this problem and try to solve this problem. If I write down I can write down everything in terms of the variables x I j, where I can choose X, the matrix X can be written as so these x I j can be my variables. So, there are n square variables now, and these thing x equal to x transpose, this can be set up for so I can write this constraint can be written like this, and this constraint, this one, as I have shown you earlier, can be written as now Okay. So, how do I construct the Lagrangian of this, so that I can write down the Karush-Kuntakar conditions? The Lagrangian, which is of course given in terms of x lambda, right, and delta, and this is now given as half summation I j from 1 to n x I j square plus, now this x a equal to b can be written as summation x I j a j minus b j. So, you can write this very basic matrix multiplication. So, it is I is equal to 1 to n lambda I b I minus summation x I j a j. Now, if you look at this, j is equal to 1 to n, and then you of course have so this is your Lagrangian, but this, if you really try to take the derivative and all those things, this will become very complicated. So, in order to make the solution look simpler, to do the solution simply, what we do is we actually put in this whole thing in form of a matrix in terms of the matrix X. So, X will now play a role. You see the complications that will arise if you are now putting a weighted thing and getting this, right. Now, let me write down the stuff. So, you know, in general, if you have a matrix X in the space R n cross n, so any X is a member of R n cross n, it can be represented, because if I can represent a matrix X if I by using a Vec operation. If it is column is, first column is A1, second column is A2, then I stack up the columns like this, and I get this n times. So, this is an n cross n into 1 vector. So, it is an n square vector, and this vector is a member of R n cross n. So, that is why it is always written like this, x is R n cross n. Then the inner product, if this is the case, then the inner product is given as follows. The inner product of two members of R n cross n is usually given as trace of x transpose y, and if x and y belong to Sn, which space of symmetric matrices, space of then x y can also be written as just trace of. Now, what happened is as follows. Now, it is very important, how do I express this thing? This part, of course, I can write this part is nothing but half x x in terms of the inner product. So, I am writing every thing in terms of the matrix. So, now how do I translate this one? This second part is translated as follows. it is written as lambda times B minus X A, right, and this means lambda B minus lambda times X A. Now, look at this expression lambda times X A. So, this inner product, if you look at this inner product is nothing but trace of lambda transpose X A. So, okay, what I am trying to mean is as follows. So, what is the trace of lambda transpose X A? Because lambda transpose X A is just a number. So, it is a 1 cross 1 matrix. So, its trace is that number. So, that is the trace of this. So, this can be again written as using the associative law of matrices, the trace of X A lambda transpose. See, this is not a symmetric matrix, A lambda transpose. So, this A lambda transpose is not a symmetric matrix, and so when I write the, so it will be, if X into Y means, so it means trace of X. So, basically this would become trace of AB is trace of BA. So, here what had happened, they have taken X A lambda transpose, then by associative law it became X A lambda transpose. So, now this is, I can write this as trace of, right. So, this simply means transpose of the transpose. If I take transpose of the transpose of the transpose. So, basically this actually means A lambda transpose X, which is same as writing as X lambda A transpose. So, here comes the nice equation that I have lambda times X of A is equal to X times lambda of A transpose. So, this is the inner product in Rn, and this is the inner product in Rn cross n, but there is an interesting relation, you see, that is the beauty of mathematics, better one. So, once I know this, then I look into it bit more deeply. Is same as we have written in the last page, trace of X A lambda transpose, and this sorry, just this step, let me have a look at it. Okay, the same thing which can be A lambda transpose X. So, which can be written as follows. This can be written as, taking up from here, it can be also written as lambda, this is already lambda A transpose transpose, so it is all right. So, this is nothing but x of A lambda transpose. So, you see there is a lot of links. So, once you have seen this, I can also write lambda x A can be also written as x of A lambda transpose plus lambda A transpose, these are matrices, by 2. So, this I leave as, so this is now a symmetric matrix. So, this is homework. This is very simple, you have to observe these things, that is all. Half of this plus half of this, that is all. Half of this plus half of this is this. Now, once you do that, then I can now write the Lagrangian function L x lambda delta as, now what about this part? This part is that we are already taking this whole thing to be true, because this part now x is equal to x transpose. So, we are now taking only symmetric matrices. Now, my problem is of this form, that I have to only bother about symmetric matrices, right. So, x is, so I have to now what I do is I make not this Lagrangian, I now just look at this Lagrangian like this. Right, and I actually now construct this Lagrangian, the first part and the second part, because now I am just working in Sn. I will tell you what is the issue. Now, let me just tell you something. What happens here is this. You might tell me, what about this constant, where does it vanish to? So, I can, because here what I have done, I have already taken x equal to x transpose, and I have set up my problem as this, the Goulet's problem is now this. Now, Sn is my whole space. Sn is a space of all symmetric matrices. Now, then what I am doing is my optimality conditions should tell me something. My optimality conditions or the Karush-Kuntakar condition is to note that basically my Sn is just like your Rn, the whole thing, that is the whole space. So, the normal cone to that whole space is actually 0. So, basically we are now minimizing some inequality constant problem. So, if I am putting whole thing in Sn, I do not need to bother to put this thing, I know that it is in Sn only, my problem is in Sn. So, I need not bother to put this thing. So, I am looking at the whole thing in from the matrix perspective, right, completely from the matrix perspective. So, my Sn is my whole space now. So, basically in Sn the problem is So, in Sn I am doing this problem. That is my problem, and on this I can now apply the Karush-Kuntar condition by taking the gradient of the Lagrangian. So, now what we do is you take the gradient of the Lagrangian and equate it to 0. You see the Lagrangian is now written like this, and then that would give you x minus a lambda transpose plus lambda a transpose. So, this is 0. So, this simply tells you x must itself be of the form a lambda transpose plus lambda a transpose. So, a is given to you, what you have to know is lambda, the Lagrange multiplier. So, here you see the importance of the Lagrange multiplier or the Karush-Kuntakar multipliers. So, now you might ask me, why are you applying Karush-Kuntakar multipliers? How do you know the KKT condition will hold? How do you know that there is a constant qualification which is satisfied? Now, in the setting of Sn, x a equal to b is a linear inequality, and hence there is no requirement of any satisfaction of a constant qualification, and KKT, there would be a KKT multiplier, right. We have shown that there would exist a KKT multiplier. I hope you remember that we have shown that every Fridtjohn point can be thought as a KKT point, because there would exist a KKT multiplier. I can always show that I can directly reach the KKT conditions if I have linear constraints, right. So, if that is the case, then here we have so this would be this, and this would give me this is the inner product, of course. Times, so this is real number into this vector, this real number into this vector. Now, B transpose A, which is B inner product A, can be written like this. I want you to check the calculation that I am doing. Now, so the last equation from this one, we have lambda transpose A is equal to A transpose B divided by 2 norm A square. So, lambda transpose A can now be put in here. So, if I put this here, I can get out lambda. So, then this is A and B. Put lambda transpose A into lambda transpose A into the equation A to get So, you can understand this will become a bit complicated when you have that particular structure Sk, Yk. You can A is your Sk and B is your Yk here, that is all. So, now putting this into x, so x would be A B transpose plus B A transpose So, this is what is usually called the Broyden, this updating is called the Broyden, Fletcher, Goldfarb, Charnow update. We will write it in terms of Sk, Yk, etc. tomorrow. So, we will write this down in terms of so in terms of the Bk1 plus Bk, but there the main norm is taken in a very different way. So, here that will give you okay. Just try to use this technique and just take the Frobenius norm of B, norm B minus Bk, and try to see whether you get this formula. So, here you see basically Bk minus 1 norm Bk, that is what you are basically looking at. Here you see the minus 1, the minus 1 is here. So, Bk Sk is your Yk, right, that is your norm here, plus, so minus part is here, plus part is here. So, x is actually your B minus Bk, Bk plus 1 minus Bk. So, here comes your AA transpose, AA transpose. Right. So, this is what's the this is called, this is your BFGS update. So, we will write down the BFGS formula algorithm tomorrow and go ahead a bit into our study of the. So, this when if Bk is PD, Bk plus 1 is PD. So, we can go ahead into our study of the problem, the Quasi-Newton method. I will take once after I finish the Quasi-Newton method, then I want to go into the issues of constant programming and I want to talk about penalty function method. I would take a very special lecture on the KKT conditions for linear programming problem. See, it is usually felt and it written in every book that I have seen is that every Fj point is a KKT point, but that actually is a misinformation in a sense that what we can show that there would exist a Fridtjohn multiplier, give me any local global minimum of a linear programming problem, there would exist one Fridtjohn multiplier which is normal. You cannot say that every Fridtjohn multiplier associated with a linear programming problem is normal. I think from my earlier lecture that would not have been clear. So, I would take a complete step by step lecture to study the linear programming problem, KKT conditions for linear programming problem or Fridtjohn conditions for linear programming problem. So, that would be a very special lecture and I think that everybody should listen very carefully, that if a constant qualification fails, the Mangasari and Fromovich constant qualification fails, even if your problem is linear, there would exist an abnormal multiplier. This is something which is very important in your understanding of optimization. Okay, so tomorrow we will continue our journey on the quasi-Newton method.